All right. So it all began with constituency parsing. And I use constituency parsing for dependency parsing, and I use dependency parsing for semantic parsing, and I use semantic parsing for discourse parsing. Well, this is my methodology. And so there are different paradigms for constituency parsing. One is, first of all, I should say that we have, you are either using supervised learning, like this article, which is also, could also be top-down approach or bottom-up approach. So top-down approach is this article, which I explain it. In the next lecture, I will explain another article from Shanghai University, which is bottom-up. So both of them are supervised learning, and sadly, I should say that in real life, we don't have labels, and crowdsourcing is expensive. We cannot do this. So, and even if we can do that, we have done it with ordinary sentences, not questions, not different types of questions, and so on. And the other approach could be, instead of supervised learning, you can use unsupervised learning, which you can use methods like, I will explain it in a different playlist, but you can use expectation maximization, Viterbi algorithm, inside-outside algorithm, and you can create a kind of generative approach. And this idea for dependency parsing is used by Christopher Manning in 2004, I guess. And this is really interesting. So if you don't have enough labeled data, no problem. Even part of a speech tag is enough. With part of a speech tag, you can do lots of things. You know, in DNA, we have CG and those things in our body. This is the language of our body. And I would say the language of a natural language is, you can use part of speech. With part of speech, you can understand lots of things, and it is as simple as these words for in a DNA, such as CAGT. So in part of speech, you can have a sequence like that. Of course, in our body, the protein could be three-dimensional, but we are not using that. But anyway, so there are two approaches to learning these constituency parsing, which is a syntactic parsing. And this approach is just the top-down approach, which I'm explaining today. So we are just using, so this parsing model estimates the conditional probable distribution of possible splitting points in a given text. So we should have a good labels and good supervised training data. So in real life, as I said, we don't have such good training data, supervised training data, and very good labels like VP, SVP, and sentence, and sometimes nothing. We should create lots of those things for all languages, so it's expensive. Okay, we assume that we have that thing, and it is enough for us to focus on a special area of our state space, so we can use this approach. So this approach is very interesting. It's just using the pointer network, and somebody uses top-down approach, somebody uses bottom-up approach, but the idea is the same. You're just using the pointing, so you're creating some boundary at each instant of time of your decoder. So the contributions of this paper are like this. We cast the constituency parsing into a series of conditional splitting decisions and use sequence-to-sequence architecture. And the other contribution is that this one, The conditional probability of splitting decisions are optimized using a cross-entropy loss, and structural consistency is maintained through a global pointing mechanism. Yeah. And also the beam search inference, along with the structural consistency from the modeling, makes our approach competitive with existing structured chart methods for syntactic and discourse parsing. Oh, by the way, this approach can also be used for discourse parsing. So the methodology is always the same. In discourse parsing, for example, we use nucleus or satellite, and we use some other thing like elaboration and those things. But the idea is the same. We are just splitting. We are splitting, and we should know the order of splitting. So this is like a sequence, and use pointer network to point at different locations. So the idea is almost the same. That's why this article solved the constituency parsing and also the discourse parsing at the same article. And the last one, the top-down parsing process. Our method can parse a text into a discourse tree without needing discourse segmentation as a prerequisite. So we see parsing as a splitting problem, as I said. And so ST denotes the set of label spans for a parse T. And we say that L of T is the label of text span. So when we say we have a span of from I of T to J of T, we should represent it by this. And also it has a label. And so this, for each parent node in a tree that spans over I and J, our parsing model is trained to point to the boundary between the tokens at k and k plus 1. I will show you an example. So the boundary-based span enjoys playing tennis is defined as 1 and 4. From 1 to 4, it spans this phrase, enjoys playing tennis. And we represent it with those bidirectional lstm, and I will show you how. So this is just the formal approach. So you have a tree, and you have a structure and labels. So L is labels. And here the idea is very simple. You're just recording the splitting points. For example, she enjoys playing tennis after embedding that. So here is typically a bi-LSTM model, and here is typically an LSTM approach, LSTM model. And so it is learning using the hidden value of decoder and also the hidden values of encoder. You can understand using above bi-affine attention of the idea of Christopher Manning in 2017 can also be used. So there are lots of ways how you are using pointer to point at different points in order to create a boundary at each instant of time. When I say instant of time, I mean, for example, time is here in the decoder first, then decoder here. So it's the standard approach. So in encoder, you're just representing the character on word. Of course, I just use word embedding. I don't use character embedding. But here in this article, they use character. So you can implement it in different ways and compare the results. Maybe if your model is simpler, you get a better. I hope you will get even better solutions. And so character embedding is a standard. So here the idea is like this. When I say span from I to J, you represent it with H, I, and J. But when you say, but each of those HI, because it's a bidirectional STM, you have forward and backward. and you concatenate them. So this is the usual trick that we see in several papers. And then you represent it and then put it into the appropriate, and you're learning these weights, W1 and W2, in order to have a very expressive, to create a very expressive power of H, I, and J, which represents the span from I to J. And finally, as I said, we use bi-affine scores. Yeah, this part is like I think this is, yes, it is inspired by Manning, Christopher Manning. I've explained this article in the, let me think, in the third lecture of my playlist for NLP in Python. In the third lecture, I have explained this beautiful article. So you see this article is also used here. It's a bi-affine connection, bi-affine attention. And even another approach for that is I've explained in the second lecture of this paper. So you can see all of them in my playlist for NLP in Python. So this is the bi-affine score. Once we have bi-affine score, so use softmax to get the probability. And then you can train it. So it's so standard supervised learning method. Nothing tricky here. Everything is standard. Also, you have a label as well. So if you go to the last slide, we have a label as well. So sometimes we should learn these. So it's not just about the boundary that you use the pointer, but also you should learn the labels as well. So here we are using, you are using multi-layer perceptron to learn the probability of each label given your span. And so everything is obvious, nothing strange. So here is training. So we have a split. I mean, just use the pointer to point to some point. What is the probability, for example, that the second, any index could be the boundary. This is normal. And also you could use the label, as I said. So by combining them, we have the total loss. So we are learning these parameters in order to do parsing, constituency parsing. So this is a top-down beam search inference. So as mentioned, existing top-down syntactic parsers do not consider the decoding history. They also perform greedy inference. With our conditional splitting formulation, our method can not only model the splitting history, but also enhance the search space of high-scoring trees through beam search. At each step, our decoder points to all the encoded boundary representations, which ensures that the pointing scores are in the same scale, allowing a fair comparison between the total scores of the candidate subtrees. With these uniform scores, we could apply a beam search to infer the most probable tree, and so on. The method generates the tree in depth first order, while maintaining top B, beam size, partial trees. I've explained this beam search algorithm in my playlist for machine learning ideas, I think lecture 10, because nowadays beam search, we have several approaches of beam search. Constraint approach, which is inspired by image computer vision and those things. So there are lots of approaches for beam search nowadays. And so here is a top-down beam search inference. So we use the syntactic tree inference with beam search, and Here we use a decoder step, whatever I've explained. And here the scores, and using the scores you understand. Sorry, not the scores. Using it for beam search, using for inference, using beam search. And finally, you see that this model, this picture says everything. It says, I've implemented a different approach of this in PyTorch, but the bottom-up approach. This approach is top to bottom. So you go here, you start splitting, record the splitting, let's say, from top to bottom. But in the next lecture that I will explain, that I've implemented it in PyTorch, it's so easy. You use it at bottom-up. Because bottom-up is less risky, I think. When you go to top-down, it is more risky. But if you go to bottom-up, it is less risky. That's the intuition behind that. And so we always start of sequence, end of sequence, and so on. So the sentences are here, and these are the things, the representations that I said. I told you how to create those things using the trick that I explained. So this was the trick that I explained. For each of these spans, first of all, you're learning them with weights W1 and W2. But once you've learned that, you can use it here in the last slide.